but doesn't matter. Okay. So we will continue with whatever we have started yesterday. I don't know why this is acting up. Okay, do you see the multi-sim screen? All of you? Do you see the multi-sim screen?
Yes, sir.
Okay, so somebody asked yesterday what will happen if we use the PNP device as a switch. So here is what we can do, and that is such a kind of circuit. You can see here this is a PNP device and the emitter is connected to VCC. Load is in collector as usual. We have already calculated the value for the base resistor, and if I run this simulation, you will see that now if I have a high, that is higher voltage, then the transistor is switched off, whereas if I go low here, the transistor is switched on. This is exactly the converse behavior of that of the NPN device. So you can see here that when it is high here, for NPN device, when it is high, the device is on, whereas if this is low, and that is actually very easy to understand. Why? Because in order for the PNP transistor to turn on, the base has to be lower than emitter by 0.7 volts. Whereas in case of this NPN device, the base has to be at a higher potential with respect to emitter by 0.7 volts. So the behavior will be exactly reversed, as we said yesterday. All right, is that okay? Is that fine?
Yes, sir.
Okay. Another thing that we would like to see here is the representation of the relay is slightly different in multisim. So you can get this device from components relay, okay, or basic virtual and virtual relay. Now in virtual relay you have three different varieties. In fact, one is normally open, one is normally closed, and the other is a combination, that is normally open and normally closed, and the pole. We'll use here normally open, so that when the transistor is switched on, we will make sure that the relay gets energized. Okay, so here is that relay. I will simply connect something at the output. For example, I will connect the DC source here, a lamp, now look at how the connection is made. It is simple here. I'm connecting this in the return path. For AC devices, normally we use the return path. Okay, so let us see if this works. See what is happening? Do you see what is happening, guys?
Yes, sir.
So if I want to
Yes,
switch on the relay, the lamp will glow because the circuit gets completed. Conversely, in case of NPN device, if this is 0, the relay is switched on, and when I assert the signal, that is make it 1, then the relay is switched off. You can see here the symbol getting changed like this. Okay, is that fine?
Yes, sir.
Yes, sir.
Okay, so one more thing I told yesterday was the H bridge. Just try to understand the concept of H bridge. So let me fire up Proteus. Now you would be surprised as to why I am spending more time here for transistor as a switch, because the reason is that it is equally important application of the BJT. All right. So just not only the amplifier application, but the switch application is very, very important, especially in power devices or power electronics, when you would be required to switch quite a couple of things as a load, you would require this circuit. Okay. So I'll just share the Proteus screen. Do you see the Proteus screen now?
Yes, sir.
Yes, sir.
See
Yes,
how the
sir.
bridge is connected? We have the PNP at the top, NPM at the bottom, like this. Okay, so this represents H, letter H. So that is the reason why we call this as the H bridge. All right. Now, as I run the software, as I simulate this, you'll see that the motor is rotating now. For that, I am asserting the signal over here as 1. Remember that whatever signal that I am applying for this PNP, an inverted signal is applied to the diagonally connected NPN. So the current
Sir, you are not audible.
So this is a very, very interesting circuit where you can control the direction of the motor. In most of the hobby projects, or let us say motorized projects, you require to have a control of the direction of the motor, forward, reverse, etc. So in that case, this bridge is normally used. Of course, nowadays people normally don't use such a kind of bridge, because integrated circuits which do have this bridge, which is fabricated on the chip itself. So many of the chips are available, but the basic mechanism remains the same. Of course, there is no protection mechanism here. What will happen if both these transistors unfortunately switch on at the same time? There will be a short circuit. You see here, a large current will flow. So there will be some protection mechanism in addition to all this, specifically using XOR gates. All right. So is the concept clear to all of you? The H bridge.
Yes, sir.
Yes, sir.
So I would want all of you to play around with this new software called as Proteus also. Don't ask me where to download it from. I won't be able to tell you that, but you can find out on the net. Okay. So we have finished the syllabus for Unit 1 and Unit 2. All right. So somebody asked the other day the concept of feedback. So we will just have a look at that concept here. Just to spice up some things, you can use this Proteus software for your Arduino projects also. Okay. Someday or today, if there is some time remaining, we will see how to use this software. Since hardware may not be available to you right now because of this lockdown and all that stuff, you can still write a couple of programs for Arduino, and then you can even simulate many of the projects. Okay, very simple projects you start with, so that will give you some kind of interesting way out to get into microcontrollers and programming. All right. So let me switch back to our notepad. And start with the feedback amplifiers. Okay, so we'll start with the feedback concept. Now please pay very close attention to this. because this is going to be one of the most important topic you will ever learn. So the concept of is the screen visible to all?
No, sir.
Now?
No, sir.
Now?
Yes,
Yes,
sir.
sir. No.
Technically, you'll learn this in some other course. Next course probably in AEC. So generally we have this amplifier here like this. Our usual signals Vs. I'm simplifying things and I'm having the load. This is going to be V out. We mark the polarities arbitrarily for the time being. Now, in feedback amplifiers, a part of the output voltage, well, not necessarily voltage or current, is fed back to the input, and this part which is fed back is called as the feedback. Okay, so we have another network over here called as the feedback network. Most of the time it is called as beta, whose input is VO. So some part of output is fed back to the input, and we are calling this as the feedback voltage VF. It is easier to understand with feedback with voltage amplifiers, so I'm using this. So now we have, for the amplifier, how many inputs are there now? We have
Two
two
inputs.
inputs, two input voltages, namely Vs itself and Vf. How they are connected, in what fashion they are connected, decides what type of feedback we have. Another important thing is that Vs and Vf, if they are connected, if Vs and Vf are anti-phase. What do you mean by anti-phase? Out of phase by 180 degrees.
180
Simply.
degrees.
Okay. Then we call this
Yes.
feedback as a negative feedback. If both of them are in phase, we call it as a positive feedback. We will not discuss anything about positive feedback. We will discuss only about the negative feedback. In fact, positive feedback leads to unstable system, whereas negative feedback improves stability. These are the characteristics of the negative and the positive feedback. As we have already seen, Vf is a part of feedback, so it is proportional to V out. In this case, we call it as a voltage feedback. Okay, so we can connect this Vf in two ways. as far as the input is concerned. Okay, so let us see how many ways in which you can do it. This is your amplifier A. This is your feedback network beta. With the output like this. So this is plus minus VO. We are supposed to have input from this. We have our usual input Vs and the output. How do I connect this? So this is mark it as plus minus VF. So the way in which I connect this is very important. I can connect it directly like this. So here it is again plus minus. So I can connect it like this. Okay, this I can have directly here. What is this type of feedback? VF. Guys, are you there with me?
Yes, sir.
What type of feedback is this? Whether the two voltages are in series or in parallel?
In series.
Series. How do you call it in series? They are in parallel. I am simply superimposing. Of course, the sign may be different. Don't get confused with the sign, because I am supposed to have a negative feedback. That is the reason why sign has to be different. But necessarily, I am connecting this in parallel. So this is called as a voltage shunt feedback. You getting this? Because Vs and Vf are connected parallelly. All right. Is this okay? Have you understood?
Yes, sir.
Have you understood?
Yes. Yes, sir.
So let us now see another variety. So what may be the other variety? Just take it here. Yes. One is parallel, other is will be
Series.
series. Correct. So this is called as a voltage series feedback. It's called as a voltage series feedback. Okay. Similarly, on the output side also, we can play around with this. Okay. Suppose, have you understood the concept of this voltage series feedback at least?
Yes, sir.
Okay. Now, if I have something like this, you have something like this, you are going to tell me what type of feedback it is now. Okay, tell me what type of feedback is this?
Series.
Okay, series. On the this side we already have recognized this as series, fine. But here some change is there. Here you will see that VF is not proportional to V out. You see this? But it is proportional to what? I out.
I
Use the same. Very, very important. So this becomes current series feedback. Okay?
excuse me, sir.
Yes.
So, but how can we like say VF is proportional to I out?
See, whatever is the output voltage here, VF,
So,
it is generated. What is the input to this beta network? It is the current.
yes, sir.
That's it. So I am generating some output voltage VF, which is actually proportional to the current and not the voltage.
So,
You getting this? I know this may sound a little bit confusing to begin with, but then you'll see that it is very, very easy. Anything in series,
yes, sir, got it.
current is same. Anything in
Yes,
series,
sir, got
current
it.
is same. Anything in parallel, voltage is same. Just remember this funda.
So,
Right? So this beta network is in series with the output. So the current is going to be same. So output voltage that is going to be generated, we'll see how to do it later on. You may study it later on. But for the time being, understand the concept that I'm able to generate VF, which is proportional to the output current. And it's very easy, by the way, that if I want to generate a current feedback, say for example, I'm having a load like this. Now I want to do something and proportional to the load current. What I will do, I will have a very small resistor here, okay, and simply monitor the voltage across this.
so
Okay, so current will be same because this value will be very, very small as compared to this. All right, so current will be same, and whatever voltage over here, in fact, it again is a potential divider itself. This VA, or whatever you would like to call this as, VA will be proportional to current.
yes, sir.
Okay, many times even the ground is not there, so it is floating. Again, the concept of floating ground, floating load and grounded load. So if I'm having like this is again the return path. I can have a resistor still here and measure the voltage across the resistor, which gives me voltage which is proportional to the current flowing through the device, through the load itself. How? Simple Ohm's law. EA is
Yes,
what?
sir.
IL into, I'll call this as R.
R.
Simple. So I'm in a position to get the feedback voltage, which is proportional to the current flowing through the load.
So,
All right.
so,
Is this fine?
yes, so,
Okay. Now the last configuration. What is the last configuration? You tell me now. What is remaining?
The current parallel feedback.
Current parallel feedback or current shunt feedback. Very good. So I'll have something like this. Of course, don't forget the load here. So this will be current flowing through this is IO. So again, VF is proportional to IO, but VF is connected in parallel with the input. So this becomes a current shunt feedback. So have you understood the 4 topologies of feedback?
yes, sir.
Yes, sir.
Okay, quickly we will see another interesting thing. What happens? Question: what happens to the voltage gain voltage gain? Which type of feedback topology is this? Yes,
Voltage series.
Voltage series feedback.
we have just now seen this, right?
So,
Now the effective voltage appearing over here, we call this as EI. Yes, any doubt, any question? So this is a voltage series feedback. All right. Now our intention is to find out the overall voltage gain, AV. It is sometimes called as AVF, that is voltage gain with feedback. Ultimately, it will be VO by VS. This is what we are interested in finding. All right. Is that okay?
yes, sir.
But what is VI? It is VS minus VF.
VF. Yes, sir.
And what is VF? What is VF? We say that it is proportional to V out. Okay.
Yes, sir. Yes.
So can I say VF is equal to beta times VO? Beta is the transfer function of the feedback network. It can be as simple as a potential divider. Okay, if this is V out, this is R1, this is R2, this is VF. So what is VF? V out into R2 divided by R1 plus R2. This factor I will call as beta. So then I get VF is beta times VO. Is this clear?
Yes, sir.
So now substitute the value of beta here, of VF here. And what is VO? What is VO? Again, I am having a gain term which is like this. AV is simply output voltage by input voltage. Is this okay?
Yes, sir.
So I can write VO as AV times VI. Okay. Now I'll get the value of VI from this equation. Call this equation 1. Substitute it here. What do I get? VO is equal to AV into what? VS minus beta VO. You can write this as VO as AV into VS minus A beta into VO. Or if I transpose this on the left hand side, VO into 1 plus A beta is equal to A times AV times, sorry, this should be AV times VS. Is that okay? Now I can find out AVF as VO by VS, giving me this as AV divided by 1 plus AV beta. We have derived the equation for output for the voltage gain with feedback. Is it okay?
Yes, sir.
So this is called as a overall voltage gain. Now you'll ask me the question, why? Why do we use beta in the first place?
Yes.
Why do we use the feedback in the first place? Okay, to answer that, open loop gain of the amplifier. This is the open loop gain. That is the gain of the amplifier without feedback. Okay. Now let that be equal to 100,000. And we do have ways of making voltage gain very, very high that you learn in operational amplifiers. So if my open loop gain is so high, and if I let beta be equal to 1 by 100, so 1/100th of the output I'm feeding back to the input, what will happen to this value AVF? Let us try to figure it out. So this will be 100,000 divided by 1 plus 100,000, yes, divided by 100. Can someone calculate this for me? Yes. Do calculate this for me.
99.9000.
99.9.
Correct. It is 99.9. All right. So I'll write here 99.9. Is that the exact value? Okay. Now suppose that because of some reasons, obviously you know that the beta or the HFE values will be different for for the same transistor. If you take different units, the beta will vary, the HFE will vary, so the gain will also vary. Agreed? We have already seen that issue.
Yes, sir.
All right. So let us say now I've used another transistor over there, and because of that I am getting AV as 1,50,000 or 150K. Now find out what is AVA. Do that. What do you get?
99.933.
99.9.
99.9.
Do you see something happening here? Suppose you take another transistor, and because of the variation in HFE, now I get a gain of only 50,000. Can you calculate AVF?
Sir, it's 99.33. 34. No,
What?
sir.
No. For AVF, for ABS 50,000 or 50K, what is the gain? Anyways, I'm getting 99.8.
Yes, sir, 99.8.
80.
99.8.
Okay. Look at these figures. Even if the open loop gain changes by 50%, my closed loop gain is super stable. Do you see? Do you realize the importance of feedback?
Yes, sir.
See, this is very,
Yes,
very
sir.
important. Even if the open loop gain changes by a large amount, 50%, in spite of that, my closed loop gain or the gain of the amplifier, overall gain of the amplifier is rock steady, which is exactly expected. Okay?
Yes, sir. Yes,
So
sir.
can we say that negative feedback stabilizes the voltage gain? With an example, I have proven that. Now again, if I make AV very large, then I can see here A into beta is very much greater than 1. So my equation is AVF becomes AV divided by AV into beta. This gets cancelled off and this becomes equal to 1 by beta. What does this tell you? Beta network we have seen is simply a resistive network which cannot change. So what does this tell you?
Yes, sir.
It is constant.
That my overall voltage gain is virtually
Constant.
independent of the open loop gain. So the closed loop gain is virtually independent of open loop gain. So no matter what open loop gain changes, my closed loop gain is going to be rock solid. All right. Yes, guys.
Yes, sir.
So have you understood the importance of negative feedback? Have you understood the
Yes, sir.
importance of negative feedback?
Yes, sir.
And now you will recollect when we started with the design of single stage voltage amplifier, common emitter voltage amplifier. What was the first statement that we said? Anyone remembering? Yes? Anyone remembers that? I said that we start designing the amplifier with largest possible gain. Remember that?
Yes, sir.
And the reason for that is I am trying to make this condition valid, so that later on you can add negative feedback and then the amplifier gain will be independent. Closed loop gain will be independent of open loop gain. Open loop gain is heavily dependent on the device parameter. So we are removing the dependency of the amplifier voltage gain, dependency of amplifier voltage gain on the device parametric variations. You getting it?
Yes, sir.
Please respond promptly.
Yes,
Yes. Yes, sir.
yes, sir.
All right. Another interesting thing about feedback is the bandwidth. Okay. So another important issue is the bandwidth. Now, please remember one thing always. There is a rule, there is a law which says that gain into bandwidth, if you multiply this, this is always a constant. This is a universal law. What does this tell you? This actually tells you that if I increase the gain, my bandwidth will reduce. If I reduce the gain, my bandwidth will increase. Simple as that. Okay.
Yes, sir.
So in feedback, what we are doing, the open loop gain AV gets reduced to AVF. So if gain reduces, what will happen to bandwidth?
Bandwidth will increase.
Bandwidth will be more. This is always going to be the situation. So if I plot, sometimes if I plot gain bandwidth like this, so this is the gain, this is the band, rather the frequency response. And we have seen that our frequency response was something like this many times, right? So if I reduce the gain, my bandwidth is supposed to get increased like this. Still reduction, bandwidth will increase. So bandwidth, as gain reduces, bandwidth increases. So an idealized curve, considering even the DC amplifier response, will be something like this. So this is the gain. Forget this part for the time being. We say that it is a voltage, it is a DC amplifier also. So this is the frequency. So as you can see, as I decrease the gain, the bandwidth changes. Decrease the gain, bandwidth increases. Decrease the gain, bandwidth increases. Remember this when we will start when we go for the next semester course, integrated circuits, linear integrated circuits. This will be important. Okay. What will happen to the third thing? What will happen to the input impedance. What will happen to the input impedance because of feedback? Let us say the network impedance is R beta. That is feedback of the impedance of the feedback network. Okay. So what are you doing here in voltage series feedback? In voltage series feedback, what you are doing? So whatever is the R beta will appear in series. Okay, this will be your R in or Z in, whatever you like to call it as, and this will appear in series. Understood? So R in with feedback happens to be your R in without feedback into 1 plus A beta. This is what happens. What can we say? That voltage series feedback increases the input impedance. This is for voltage series feedback. Is it good or bad? Guys? Hello? Guys,
Yes, sir.
is this a good thing or a bad thing? Increase in input impedance. Yes? Increase in input impedance is a good thing or a bad thing? Come on, answer me. Let it be wrong.
Sir, bad thing.
Bad thing. Do you remember once when I said for ideal voltage amplifier, input impedance should be equal to infinite. Output impedance should be equal to 0. So if I have the feedback, if input impedance increases, whether it is going towards the better side or the worse side. Guys, do you remember this?
Yes, sir.
Yes or no? Why input impedance of the voltage amplifier, ideal voltage amplifier, should be infinite, and why output impedance should be 0? Please pay close attention. I'll repeat this. If you have an amplifier, voltage amplifier, you have this RS usual thing. This is your input impedance. Load, output impedance. See what is the effective voltage appearing here. Isn't it like this? You have a Vs, you have RS, you have the impedance of the device, of the amplifier,
Yes.
and this is your Vi, which is appearing at the input to the amplifier. Are you able to see this?
Yes, sir.
Yes, sir.
So, what will happen if the input impedance is less or comparable to
voltage,
RS.
sir, voltage drop नहीं होगा तब.
What? What will happen?
Voltage drop would be less.
Will be less.
The
This is the
voltage.
again the concept of loading effect.
Yes,
Remember,
sir.
loading effect won't leave you anyways. So what is happening? If Zin is less as compared to RS, let us say worst case Zin is equal to RS. In that case, what will happen is Vi will be Vs by 2. So input to your amplifier itself is half. So the voltage gain is going to be affected. You are only feeding half of the input voltage, na?
Yes, sir.
Yes, sir.
Now imagine if Zin is very large. So Vi is Zin divided by Rs plus Zin. So if Zin is very large as compared to Rs, what will happen? Vi will be nearly equal to, this should be Vs.
Yes.
This will be Vs. And you will get the maximum output voltage. Okay? So we require that ideally voltage amplifier should have input impedance as infinite. Practically it has to be very high.
Okay, sir.
Okay, sir.
Okay? Have you understood this? Again, there will be a loading effect here. We have already discussed loading effect at length. Alright? What about output impedance? Okay, anyways, let us complete this first. What about output impedance? Voltage across your, this is going to be V out. So whatever is your input, whatever is your output voltage, actual output voltage, I will call this as VO dash. And then I have the Z out. And then I have the RL.
RL.
This is going to be your V out. Same thing, no? Here V out will be V out dash into, yes, RL divided by
ZO plus Z.
ZO plus
RL. Now, if I want the entire V out to be available at the output, VO dash to be available at the output, what should be the condition?
ZO should be very less.
ZO should be as small as possible. And though we come to conclusion that ideally Z out should be equal to practically
Very
you're getting
small.
this? This is very important. So with feedback, I'm actually increasing the input impedance. So whether it is good or bad,
Good.
it is good. But when we talk about only voltage amplifiers, remember my discussion is restricted only to voltage amplifiers. For current, it will be different. What about RO? Look here. Okay, where was that? Voltage series feedback. Okay. So what about RO? What will happen to RO? This was your Z out. This is the impedance, input impedance of this guy. Call this as R beta, whatever you would like to call it as. So input impedance, output impedance of this amplifier and input impedance of the beta network. They will be in series or parallel.
Parallel.
They will be in parallel. Parallel combination of resistors. What happens?
Equivalent resistance decreases.
Is less, isn't it? So can I say that R out with feedback is equal to R out with feedback? It gets divided by a factor of 1 plus A beta. So output impedance increases or decreases? With voltage series feedback, output impedance increases or decreases? This is without feedback. Gets divided by 1 plus A beta. So whether it increases or decreases? Guys, come on. Guys,
Decreases.
so
Decreases.
whether it is good or bad?
Sir, it's good if it decreases.
Yes. So we have very nice effects of the feedback.
Feed-
That is the negative feedback. We have very good effects specifically for voltage amplifiers or voltage series feedback. We have very good side effects. That is the reason why negative voltage series feedback or negative feedback is preferred. Of course, this is not always the case. We don't have enough time for that. Neither we have there is scope for that. But in case of voltage feedback, it can be series or parallel. Always the output decreases. Okay. In case of current, whether it is series or parallel, R out increases because beta network is in series with the output.
Sir, you are not audible.
The input impedance increases in shunt or parallel. RINF decreases. Just remember these things. Okay. So with that,
Yes, sir.
I will stop as far as the feedback is concerned. There are additional feedback, additional effects because of the feedback, but you may not be able to understand those at this point of time. But this should be a good start as far as the concept of feedback. So I just want to give you a big picture. Why we started designing the voltage amplifier, common emitter voltage amplifier with largest possible gain. Why did we do that? The answer is this: because ultimately we would be employing negative feedback, and then if open loop voltage gain is very large, in that case I can make the overall voltage gain independent of the device parameters. Okay?
Oh,
Is that fine with all of you?
yes, sir.
Okay, so please revise the concepts. I think that you are forgetting so many things. Don't treat it like any other just online lecture like that. Okay, you have to
Actually,
keep
sir,
on revising. Yes.
before starting this, sir, I asked you question, sir, कि अगर like हम अगर बीटा की values change करेंगे सर या फिर और भी जो factors हैं तो सर उससे हमारे बाकी की चीजें change होंगी तो सर इसी के लिए for this reason only we use this negative feedback.
Exactly. Exactly. That is what we are trying to say for such a long time, that we want to make the voltage gain, overall voltage gain, independent of the device parameters. Device parameters can be specifically the HFE.
Okay, sir.
I'm not referring to beta because this beta, that beta will get confusion. You'll get confused over there.
Sir, got
That is the reason why I'm using HFE. Okay.
yes.
Yes, sir.
Any other doubt? Any other question? If you guys are interested in one of the lectures, I will tell you how to simulate Arduino board on Proteus. If people are interested in one of the
Yes,
lectures,
sir.
that would be. Shall we do it on Monday? Just for fun.
Okay,
If you
sir.
want to-
Okay, sir.
Yes.
Yes.
Yes, sir.
Okay. So that will get you started with Arduino also. All right, we'll stop here for today.
Thank you, sir.
Okay, thank you so much.